All right, it's 2:02 now. Let's get started. So, hello everyone. Welcome to Ask Seminar series. This is John. I'm the seminar coordinator. So, I will be coordinating this seminar with Kazi, our communication specialist. And also join us is our director, Naz Peter. So, Naz will be introduce the speaker. Just so you know that this seminar is being recorded and we will post a video on our YouTube channels. And just as a reminder, we'll have an in-person seminar, a special one this Thursday. So please feel free to come. And before the speaker gets started, I'm going to hand this ball to our director, Naz Peter. So Naz, please go ahead.
Thanks, John. Thanks, John, and welcome to our seminar speaker today, Professor Eric Kort. I'm very happy to have Eric give this talk to us today. And just by way of a brief introduction, Eric is the Associate Chair of the Department of Climate and Space Sciences and Engineering at the University of Michigan. He's a professor at Michigan, where he works on various things that we humans put into the atmosphere, greenhouse gases and many other good and bad things. And Eric works on our ability to quantify what we're actually doing to the atmosphere using observations both from the ground and space. Eric got his bachelor's in physics from Pomona and later on a PhD from Harvard, and he came, his route went via JPL and Caltech, and he is now at Michigan. And he's going to talk to us today about his work on quantifying emissions and how we use observations to help us with that. So I think that's enough for me. The floor is yours, Eric.
Thank you for the kind introduction, and also thank you for the invitation. It's always a pleasure to be able to talk about my work with a engaged audience. So yeah, today I want to talk about using space-based and airborne observations to study both direct and indirect human impacts on atmospheric composition. And actually, this photo I have here prelude some of what I'll discuss. This is a photo taken from the field when we were doing aircraft sampling of agricultural emissions. And actually, this is a series of agricultural fields that actually at the moment we took this photograph was a bit flooded. You can actually see a little bit down in the bottom where the farm structure is, and there's kind of muddy water all around it. But before I go into all the interest in science, I want to kind of thank and acknowledge the people and organizations that make this type of work possible. First, a lot of the type of work I'll show here, and often a lot of work in atmospheric chemistry, is collaborative. I'm fortunate to have been able to work with a number of wonderful students, postdocs, colleagues, scientists, engineers, pilots, to be able to do this type of work. In particular, I want to call out research scientist Jenny Plant, postdoc Taylor Adams, and students Erica Whiting and Daniel Huber as people who have led a lot of the work I will show here today. And of course, this work has been funded both by federal programs as well as from private foundations. And really, this type of work is not possible without that type of support. And if that kind of support goes away, this type of work will not be able to continue in the way that it has in the past. All right, let's get into the fun stuff now. The human impact on our atmosphere is large, right? And saying that is not a surprising statement, but I want to bring our attention to not only is it large, but it is changing rapidly. And the scale of the human enterprise now is such that actually when we have regulatory or technological or economic or a combination of all of those things changing, we actually can change our emissions to the atmosphere in rapid and short time periods. There's a number of examples we could go into for this. The one I'll show you today is one I consider a positive one. This shows satellite measurements of nitrogen dioxide, or NO2, over the US in 2005. Why do we care about NO2? Well, it is a primary pollutant, so it's not good for us. It's also a precursor for tropospheric ozone. And you can see there's quite a bit of red centered around where there tends to be kind of power plants or urban areas. If we just skip ahead a mere 6 years, there's far less red in this plot, right? So same satellite, same measurements of NO2, far, far less NO2. And this change came about because of a combination of regulatory, technologic, and economic pressures. These types of changes are happening across the landscape, right? So this is a positive example. I could have shown a similar example that might be not quite as positive related to methane emissions and oil and gas. So as these human activities change, we can really drastically change our inputs into the atmosphere in short order. We then know that actually atmospheric chemistry and ecosystems can dynamically respond to these anthropogenic pressures. And that's both in response to the direct emissions, right? If you change the amount of NO2 into the atmosphere, the chemistry will respond, the amount of nitrogen deposited into ecosystems will change. But we also know that chemistry and ecosystems change in response to climate change and the larger forcing that's happening. And all of those dynamic responses further change atmospheric composition. So if we really want to understand our current and future climate and air quality, we really need to understand the fundamental controls of the atmospheric system and how they respond to human forces. And this is really what my research group is focused on. So we tend to use observations as the foundation for our analyses. We use measurements from space, from aircraft and the ground to really study greenhouse gases and pollutants from local to global scales. We'll tend to combine these observations with models to really understand the key controls, what's controlling emissions, what's controlling the resultant atmospheric processes, and really try to look at what's happening with climate, air quality, and potentially inform societal response and mitigation efforts. Today, I want to touch briefly upon 3 examples of work that's going on in my group, which is really trying to advance our understanding of emissions and impacts of methane, nitrogen oxides, as well as refrigerants. So let's start with methane. Methane is one of my favorites. Methane has been an interesting problem that's been really challenging for us as a community to understand. So first, why do we care about methane? Often the primary reason you hear is it's an important greenhouse gas. It also is a precursor for tropospheric ozone and an important source of stratospheric water vapor. The greenhouse gas component is often what's most discussed, and that's for good reason, right? If we look at the growth in atmospheric methane since pre-industrial, about a half a degree of the observed warming on our planet can be attributed to increases in methane. But methane is different from some of the other long-lived greenhouse gases. It has a relatively short lifetime of about 9 years. That's primarily because methane is removed through chemical reactions with the hydroxyl radical in the atmosphere, also known as OH. Right? And so there's this removal process that takes methane away in the time period of about a decade. That hydroxyl radical sink is the dominant removal process. It's roughly 90% of the methane is removed that way. The largest sources into the atmosphere, the largest one is actually a natural source that's susceptible to perturbation by man, but is wetlands. We then have fossil fuels, agriculture, and waste management, or landfills, as the next biggest sectors of emissions to the atmosphere, and those are all driven by humanity. On the right, I show here a composite figure. In blue, it shows the Law Dome ice core record for the last about 2,000 years. What you see here is that methane levels in the atmosphere were about 650 parts per billion, and were fairly stable at that level in a pre-industrial period. Then, of course, we see this rapid rise in methane, and now we have methane levels that are approaching 2,000 parts per billion, right? So we've seen a large increase in methane levels in the atmosphere. But it hasn't been just one smooth continuous rise. The inset shows a zoom in on the last 40 years or so, where we've seen real variability in the growth rate of methane in the atmosphere. There was kind of stable growth occurring in the 80s. In the 90s, there was a slowdown in atmospheric methane's growth. From 2000 to 2007, it stabilized. It seemed like methane was no longer growing in the atmosphere, and maybe we had reached a new steady state level. And then we had renewed growth in 2007. And then in recent years, particularly in about 2020, 2021, 2022, was really what we call the accelerated growth years, when very high growth rates of methane occurred in the atmosphere. Now, all this variation in growth is what happens when you have changes in the balance between sources and sinks. So if you increase the sources or you reduce the sink, you'll get an accelerated growth rate, and vice versa. And really, this growth and this variability in growth is controlled by kind of 3 larger categories: people, which is really related to what we're doing with fossil fuels, waste, and agriculture; ecosystems, and in this case, it's really wetlands and tropical wetlands that are that large source that potentially can be dynamic in time; and then chemistry. The OH sink is a very large sink. Even relatively small changes in that can change the growth rate. So as we look back on these decades, there's a variety of theories that at times conflict, trying to explain the different accelerations and decelerations in growth in methane in the atmosphere. Today, I want to focus a little bit moving forward, looking at the recent past, and say that our observational capabilities really have been improving in this space. And I think this is empowering us to do a much better job to understand growth and growth rate moving forward. And today I want to focus on two things we've been working on in my group. One is assessing what the role of anthropogenic emissions, particularly cities, and how much that's contributing to recent growth rate and acceleration of growth rate. And then ecosystems, particularly tropical wetlands, and trying to understand the role those might have played in the recent surge. So that's what I'll dive into in more depth right now. So let's start off with cities. So why cities? Well, we know people live in cities, right? That's what makes them a city. But today it's a little more than half of the global population that lives in cities. Projections can estimate as much as 80% by 2050. So there's a lot of people in cities. With all these people and the concentration of anthropogenic activities, we get a concentrated source of methane. And this is primarily related to natural gas end usage in cities, related to wetlands, or sorry, not wetlands, landfills in cities, and wastewater treatment that occurs in cities. And these concentrated sources of methane, in some ways, are observationally an opportunity for us to measure and understand what's going on because we get bigger signal to noise when we get a concentration of emission sources. So we started to pose the question, well, can we quantify and track these urban methane emissions? Can we do so from space so we can do this around the globe? And if we can do so, then we can try to ask questions like, are cities meeting their emissions pledges? And I'll talk more in a second about the C40 network of cities. But we also can answer this big question that really motivates what I just talked about, which is, can we inform global methane trends? Are there changes in urban emissions that are then mapping into the global methane trend and explaining part of that variability we see on the global growth rate? For assessing whether cities meet their emission pledges, we'll talk more later about these C40 cities. There's right now about 96 cities that are members of this C40 network. This is basically a network of mayors that have pledged to reduce climate-related emissions. And there's a variety of different pathways and approaches that this can be done. But pertinent for this is that there's a minimum of a 34% reduction by 2030 of methane, and they encourage people to get down by 50%. So these are pretty ambitious methane reduction targets that these cities have. How can we go about quantifying and tracking emissions from these cities? So we started out using the airborne observation. So this is a little bit older data now. This is from measurements we made as part of the East Coast outflow campaign we did with NOAA in 2018, also known as ECO. And the idea was pretty simple. It's to fly low and slow around major US urban centers. And this was with the NOAA Twin Otter aircraft. So it's a relatively small aircraft. We did have continuous measurements of methane, carbon monoxide, carbon dioxide, water vapor, and ethane on this plane. And at the time, it actually turned out to be what was the most extensive study of methane emissions across different cities. And the idea was really to fly around these urban centers, in particular sampling downwind, and to capture what we would call the urban plume. So the elevated pollutants that are coming out of the concentrated urban core. And when you do this, you can see strong correlations. And in this case, I show an example here that shows methane on the y-axis, carbon monoxide on the x. And even though these gases are not co-emitted, right, the CO is largely coming from cars on the road, whereas the methane is coming more from the landfills of natural gas. These gases mix together in the atmosphere, and when we sample this urban outflow, we see very nice correlation between all of these different anthropogenically emitted gases. And the idea is we know carbon monoxide and carbon dioxide emissions far better than methane. So if we measure these nice correlations downwind, we can actually use these ratios, and I show an equation here on the bottom, where you can use the ratio combined with the known emissions of carbon monoxide, accounted for different molecular masses, and get the emissions of methane out in a very nice database method. So we could do this with carbon monoxide. We could also do it with carbon dioxide as an independent check. And in the case of the airborne data, we also used continuous ethane measurements to then be able to attribute if the methane is coming more from landfills, which is more of a microbial source that doesn't produce ethane, or more from the natural gas system where there is ethane along with that methane. When we did this, and I'm not going to go in great detail, but if you aggregate it together for these 5 cities, the yellow on the left shows our observed total methane. The yellow on the right shows the US EPA inventory. You see that emissions are a little more than twice as high as reported in the EPA inventory. When we use the ethane to attribute to natural gas, we see the blue natural gas component is quite a lot higher than that estimated in the EPA inventory. Right? And so this showed that across these older East Coast cities, there was quite a bit higher methane emissions than estimated in inventories, and it seemed to largely be based on natural gas. Now, this is great, but it's hard to fly the airplane in 5 cities, let alone to fly in dozens of cities. It's not easy to fly across the US and certainly not across the rest of the world. So can we do this from space? Can we actually do this that way? And we decided to try to use the TROP-OMI satellite to do this with a very similar approach. Why is that? Well, TROP-OMI makes measurements from space. So this is a European project. It has a shortwave infrared band where measurements can be made of both methane and carbon monoxide. This is really nice because it means you get a simultaneous measurement on the same spatial grid of these two gases. And now you can use a very similar principle to what we did with flying the aircraft and sampling the downwind plume. You can look at the enhancements of methane compared to the enhancements of CO and combine this to then look at the ratio and combine with the carbon monoxide inventory to get methane emissions. To evaluate this approach, so we first kind of developed a set of procedures to do this. And we actually use individual day observations from TROP-OMI. And this shows one example of one day over New York City, methane on the left, carbon monoxide on the right. There tends to be higher levels of both these gases around the urban core and in kind of the downwind region on that day. We do this with individual daily data. We go through and we filter for clouds and so on. And we basically get enhancement ratios, which we can translate through that same equation as we showed before. We evaluated this by actually doing model simulations to see if this retrieved accurate emissions relative to model simulations. And we also evaluated against the aircraft data for some of these East Coast cities that we actually also had aircraft data, and things look pretty good. I won't go in more detail, but there's a paper on this. So since this looks pretty good, we can start to expand out. And first we did by expanding to a handful of more cities in the US. So this shows methane emissions estimated with this TROP-OMI measurements from space. You can see we have some of the cities we saw before: Boston, Philadelphia, DC, and Baltimore. All of our observed emissions are the gray bands. The EDGAR inventory is in orange and the US EPA in blue. Those are very similar. You can see the emissions tend to be roughly twice as high as in those inventories. But now we've added cities that have very different infrastructure and age profiles. We have Portland, we have Kansas City, we have Atlanta. And we see that this urban methane emissions tends to be elevated relative to the inventory, kind of in a widespread manner across the US. Interestingly, Kansas City is the city that has very little natural gas infrastructure, and that's the place where we tend to see the best agreement between the inventory and the satellite-based method. What I want you to take this is that we now think we have a robust space-based method to be able to assess urban methane emissions and see how that will evolve. And so what we're doing is we're building up now from this case in the US and a handful of cities to actually doing a global analysis and doing this for 2019 to 2024. So using a very long time series of satellite data to start to evaluate if we see changes or variation in urban methane emissions. So I'm showing here a map. This is work led by student Erica Whiting, where there's all of the C40 cities that we're trying to study are shown in different colors here, where the colors correspond with the C40's network definition of different regions. So they define different regions, and we're simply measuring their cities in this way. The black dots actually represent cities that we're measuring that are not participating in the C40 or other climate pledges. So the idea here is to evaluate cities that are participating in climate pledges and cities that are not, and to see if any differences emerge. I show you just a couple insets here. This shows New York City again, and then Delhi, India, where again, you can see the elevated methane and carbon monoxide that correlate pretty well coming out of that urban core. So when we do this, we're looking at about 70 cities. The population of these cities is over 1 billion people. And if we sum up the emissions from all these cities from our quantification, it's about 10% of the total anthropogenic budget. So no, this is not the biggest source of methane to the atmosphere, but it is a pretty big part of the anthropogenic budget. So if we can start to understand what is going on there, it can be informative towards the global growth rate. We can start to look at individual cities. So here I'm showing just 2 sample cities from each of these C40 regions. And it depends a little bit on the city and how much data we get, but we think we can track individual cities' annual emission changes on the order of about 20%. So the top row here shows the methane to CO enhancement ratio. So this is the direct observable from the satellite. And you can see that in many cases, we can observe this with quite high fidelity, and changes in that ratio can be mapped very well from space. And then in the bottom, we show the translation into methane emissions. We've normalized it to the 2019 year, so you can see the relative change over that time, and we put the emissions magnitude there. So you can see on the top, there's methane to CO enhancement ratios that are as low as something about 0.5 and are high as almost 3. So that's kind of the range of what we tend to see for emission ratios. When it gets very low, it tends to be because there's a very elevated carbon monoxide emission. So Shanghai is an example for that. When it gets very high, it's a combination of often elevated methane and relatively lower carbon monoxide emissions. You can start to see when you look at this that a lot of the individual cities we look at tend to have increase in trends, but not all of them. There are examples of individual cities where there are decrease in trends, and in some cases, significant decrease in trends. To really assess how the climate fluidity pledges are working, we consider this on regions. So based on their definition of different regions, we kind of looked at how are the methane emissions evolving in time. What we see here is that most of these C40 regions actually show emissions that are either relatively stable or growing in this time frame. Europe is the kind of notable exception here, where you actually see a decrease in this time frame. As a whole, I would say it doesn't seem like things are on pace to drop emissions by more than a third by 2030. This would require a very rapid drop in emissions. Now, it is, of course, possible this could happen. And for some of these cities, the pledges that they've made, the actions that they want to take to reduce emissions may not have yet taken effect. So this still could happen. What happens if we lump this up globally, and what can we say globally about this? Here's all the C40 cities and all the non-C40 cities. So blue is C40 and red is non from 2019 to 2023. What you see here is there's a pretty similar pattern going on in the cities that are participating in climate pledges and ones that are not. So at this point, it seems like emissions are not yet matching the ambitions. As I said, it's possible that some of the actions might still come to actually reduce these emissions, but it would require a pretty rapid drop now. And if we have a continuity of observations like this, we should be able to observe and track those drops. We could, of course, try to dive down into more detail on some individual cities. This method isn't great at attribution, so it's not the best to inform exactly where the inventories were wrong, but complemented with other observations can really start to answer those questions. In terms of the global methane question, which is really one of the major things that drove a lot of our work here, this is a relatively modest contribution to this kind of recent methane surge where we saw these very high growth rates in the early 2020s. You can see there's kind of a relatively small and steady growth in the urban emissions here, which will contribute, right? It's going to be less than 10% though of the annual growth that we see in methane in the atmosphere. So it's an important component to identify, but this does not explain why 2020, 2021, or 2022 were such large growth years for methane. So can we better understand what might have driven those growth years for methane? And let's switch to wetlands to try to see if we can explain this. So wetlands are the largest source of methane to the atmosphere, right? So as a large source of methane to the atmosphere, this is perhaps a good candidate for explaining large changes in growth rate, right? A relatively smaller change of a very large source can actually be seen as a growth rate change in an individual year. Additionally, a lot of concerns have emerged that maybe the accelerating growth of atmospheric methane could be linked to tropical wetlands and represent a climate feedback where we have warmer and wetter tropics emitting larger amounts of methane that lead to a warmer and wetter tropics that then emit more methane and so on. One of the real challenges here in a lot of the work that people have tried to do in the tropics is that there's really limited observations of methane in the tropics, and it's really a core shortcoming in past assessments. What we've tried to do here is try to look at, rather than the limited methane observations, is to consider the hydrological drivers. So we know one of the major drivers of tropical wetland emissions is water and inundation. So what if we look at observations of this? Can we start to understand or explain changes that might have happened in this time period when methane grew so rapidly in the atmosphere? So what does water tell us? We started by primarily using a new inundation product. So this is an inundation product built with Cygnus satellite data. So Cygnus is a constellation of satellites that's been supported by NASA. That project actually was designed to look at wind speed in hurricanes. So it's a constellation of satellites that actually look at scattered GPS signals off of the ocean surface and by changes in surface roughness and for wind speed. By doing this out at GPS wavelengths, it means you can see through clouds and be able to see through a hurricane. Well, it turns out this scattered signal is actually a very robust way to be able to identify water or land on surface because they scatter very differently. So as part of a joint project on Cygnus, Cynthia Gerlin-Safdie's group at Berkeley put together this Berkeley RAC product. So this is a nice inundation product, and it enables us to look through clouds and through canopy, and with this constellation of satellites in the tropics, get quite high spatial and temporal resolution of inundation. So this product has been put together. We started to assess it in a lot of different ways, and we see features of seasonality and interannual variation that some of the earlier products didn't really capture. And a lot of those products were challenged to be able to see below clouds and canopy. I show it as an example where we see large differences is the Sud wetland in East Africa. So here in red shows the Berkeley RAC product, and you see this very large seasonal cycle in the inundation there, as well as actually growth in this time frame from 2018 into 2023. And actually, a number of different independent proxies and observations suggest that there is this very large seasonal cycle in the Sud, and there is this growth that has been occurring in that region. Some of the more traditional products are in black and in blue, and they don't really capture the same seasonality or growth. An alternate new product that has been put together, the GEMS MC product, is shown in purple at the bottom. It does seem to capture the same seasonal cycle and probably also the growth, but it has lower inundation magnitudes, the differences between the different products. So then we ask, if we have this new inundation product, what if we drive an ensemble of wetland methane emissions models? And what do we actually see over this time frame? Do we see a surge or a pulse of emissions that are coming out of the tropics driven by changes in inundation or temperature or other factors? Or do we see something else going on? And so we drive an ensemble of wetland methane models. This is with Anthony Bloom at JPL and the wet charts model. We also drive them independently with precipitation data. So we're doing multiple drivers here, trying to see what does inundation suggest is happening in this time frame. And I will show you one other figure here before I jump ahead, which is, yes, we see high inundation variability and increases in the Sud, but if we look across the whole tropics, the red here shows the inundation fraction across the tropics in this time frame. We actually see a slight decline in tropical inundation with this Berkeley RAC product. I mean, you can see that the other products do not actually show a secular increase or a surge as well. So seeing that, you might find it not surprising that when we drive this ensemble of wetland methane models, we do not see a pulse or surge or large increase in emissions in this 2020-2021 timeframe. We actually see a slight decrease when driven with inundation, and really pretty flat static emissions when driven by precipitation. The red shows the ensemble models driven by inundation, and the blue shows it driven by precipitation. We actually also independently ran a process model that was constrained by GRACE observations of total water and also could not explain any kind of surge in this 2020-2021 period. So that really tells us two possible things. One is wetlands are perhaps not contributing to the surge, and it was a different imbalance in emissions or removal that led to this really elevated growth rate in recent years. Or some tropical wetlands emissions are not controlled by water the way our current models and understandings thinks, right? So if, for example, some wet tropical wetlands had a higher temperature sensitivity and carbon sensitivity that's not captured by any current models, that could potentially explain why there would be a surge in emissions and our wetland models wouldn't capture that. This will require more work to try to disentangle. I think it really exposes a fundamental gap in our understanding of methane controls, because either a different source or sink is varying in a way that we are not capturing, or wetlands are behaving in some way that we are not accurately capturing. So we haven't gotten there yet for methane. We haven't closed the loop. Observations are really helping us get closer and getting further there, but we aren't there yet. And really, to really nail this down, I think we're going to need more and improved tropical observations to really say something strong on this front. All right. Let's switch a little bit gears here and talk a little bit about nitrogen. And I'll talk about a couple different nitrogen gases. First, let's talk about NOx, which is shorthand for NO and NO2 together. This plays a really central role in governing air quality, right? So NOx is a primary pollutant itself, as well as a precursor for tropospheric ozone. And it's also important for controlling the atmosphere's oxidative capacity. N2O, or nitrous oxide, really impacts both stratospheric ozone levels. So this is a more stable gas. When it makes its way into the stratosphere, it can contribute to stratospheric ozone depletion. And it also, with a long lifetime in the troposphere, is a pretty potent greenhouse gas. And actually, often the N2O and NOx are studied by fairly different communities. Sources for both NOx and N2O are changing pretty dynamically right now. And really what current emissions are and what future emissions will be and the resultant atmospheric impacts of that are not very well known. And I did open up today showing how fossil emissions of NO2 here, right, have decreased rapidly in some parts of the world. Meanwhile, agricultural emissions are actually increasing in most places. And I show on the lower right, this shows model estimates of anthropogenic N2O emissions from croplands, right? So these tend to be increasing, where basically we are growing more crops with more fertilizer as time goes forward, and the nitrogen emissions from those soils are increasing. As fossil NOx starts to go down, these agricultural NOx emissions start to become more and more important. As N2O emissions continue to increase, they really are quite important for stratospheric ozone as well as for climate. So how can we study these agricultural emissions to better understand what's happening for nitrogen? And can we do so from space so we can actually do this at agricultural regions around the world and not only in limited places we can set up ground or airborne measurements? So a student working with myself and Allison Steiner, Daniel Huber, started to look at this a couple of years ago and really was finding that we could really start to observe agricultural soil NOx emissions from space. So this shows the Mississippi River Valley. So on the left, you see on Memphis, Little Rock, and Jackson. So these are some different small cities along the Mississippi River in the US. The Mississippi River cuts roughly down the center of that image. The kind of less bright green, the brighter, more white region that's by the river, this is all agricultural fields. This is a pretty big agricultural domain. In the middle, we show NO2 observations from the Tropomi satellite before a rainfall event, and then 5 days after on the right. And you see a lot more red on the right, and a lot of that red tends to be above and downwind the agricultural fields. And we think this is a pulse of soil NOx emissions that has come out in springtime on these fertilized soils after it has rained, and you get this pulse of emissions. So we really think we can start to see cropland emissions from space with observations from individual days. So this is not average data, this is observations from individual days. And then we can integrate this data with models to start to quantify emissions and understand more about process. In this case, if we do a very simple box model, we can look over multiple seasons and see the seasonal cycle. So here the black, the red, and the blue show estimated soil NOx emissions from satellite data in a box model. The difference between the different colors are different simple assumptions about lifetime of the gases. The gray dashed line shows the BDNSP modeled emissions of NO2 into the atmosphere. And we see this very strong seasonal cycle with peak emissions in spring. This really coincides with fertilizer application and increase in soil temperatures and water availability. Basically, you put a lot of extra nitrogen down in the soils, it then gets warm, it gets wet, and a lot of it comes out as nitrogen oxides. The emissions we see actually are higher than that predicted in the BDNSP model. We can also start to aggregate and look at individual days and individual events and start to get maybe a more mechanistic understanding of what's happening. So here what we've done is we've identified multiple different kind of what we would call pulsed emissions events out of these soils from the satellite. And we align them up where the kind of peak NOx signals in the atmosphere line up on day 0. And in all of these cases, what we see is there tends to be rainfall happening some number of days before. So it rains quite a bit. The soils get very wet and saturated. So we see the SMAP soil moisture is very high. It's wet and saturated. Then as time goes by, that soil moisture starts to decline. Things start to dry out. And when you end up at what I would call a moderate soil moisture value, somewhere roughly halfway between as wet as those soils get in that region and as dry as they tend to get, is when we tend to see the peak emissions of NOx into the atmosphere, right? So the satellite's actually not only enabling us to see emissions from croplands and kind of quantify it in aggregate, but we can start to look at individual events and link it to process. And indeed, Daniel Huber actually followed on, and I won't go into detail today, but did some more analysis to actually improve emissions model representation to take into account these features, and then WRF chem modeling to actually look at the atmospheric air quality impacts of these types of emissions. So that's for NOx. Now, what about nitrous oxide, right? Can we do something similar here? Now, the problem for nitrous oxide is that it's long-lived in the atmosphere. So there's very small signals from cropland emissions on a really large atmospheric background. And I'm showing some data on the right from some aircraft flights we flew in Iowa, looking at cropland emissions of nitrous oxide. And you can see the variability we see is about a ppb on a background of 340 ppb. Right? And a single ppb signal is a relatively large one that we see on that background. That's a very small signal to try to detect remotely. And right now, we're not anywhere near doing this from space for nitrous oxide. So are we all out of luck, or are there other ways we can get at this? Well, we've been exploring whether we can get at this indirectly from NOx. We know that emissions of N2O and NOx from agricultural soils are related. To put it very simply, if you put a lot of extra nitrogen down as fertilizer, and then your soils are warm and they come to moderate soil moisture values, you will tend to get excess amounts of N2O and NOx out of those soils. So can we use this relationship then to use satellite NOx to infer N2O emissions? And to do this, we went through multiple steps. So first we tried to determine N2O to NOx emissions ratios at commensurate spatial scales that satellites make measurements. And that's important because most of the historical work done on N2O and NOx emissions have been done at a chamber scale. And they find quite a lot of variability and complexity in that relationship. But what we observe from a satellite is the aggregation of not just a single meter, but it's many, many farms that are aggregated together, often with many different crops, with some parts that are wetter, some parts that are drier. And so is there a robust N2O to NOx emissions ratio we can determine that actually we can then apply to satellite observations that infer space-based NOx emissions that we can then combine and infer soil N2O emissions? So this is what we tried to do. We started out looking at aircraft data, and we actually are going back in time a little bit here to CalNex, which happened about 15 years ago now. But it's one of the only campaigns where both accurate and precise measurements of N2O and NOx were simultaneously made downwind of agricultural fields. And in this case, it was in California. So we focus on all these flights that were made in, around, and downwind of agricultural croplands. And then we try to assess, is there a robust emissions ratio of N2O to NOx? We do this by looking actually at the data in multiple different ways, from very simple, where we just aggregate the data and find a slope, like what I'm showing you here, to actually looking at individual kind of emissions plumes that are coming off of aggregated farmlands and determining a whole population of emissions ratios of these things. Turns out we can do this a bunch of different ways, make different assumptions about chemical loss, and we actually get a pretty similar distribution. So we end up getting a distribution of emissions ratios that we then want to apply more widely. So now we've gotten this from aircraft data taken quite a while ago in California. The way to kind of start to test and evaluate this is we say, well, what if we take and we test the satellite approach against regions where there are independent nitrous oxide observations, and we do this in regions that are different from California. So first, we use the satellite to identify and quantify cropland soil NOx emissions, and we're doing this for 3 locations that other studies have been conducted. So there's a different group conducted a study in Iowa with ground-based chambers for a couple of years ago. That's the Lawrence paper. So we look at a box that encompasses their study domain and try to look at emissions in that domain. And then my group in past years has done studies with aircraft in the Mississippi River Valley, that's Kavakaria, and in Iowa, that's the Dot-Cheech study, where we also independently assess N2O emissions. So we could have a check. We can try to derive N2O emissions from satellite NOx. So what we do is we do satellite NO2 observations from Tropomi. Those are shown here for different boxes. We then use a box model to derive the NOx emissions. We then can combine that box model NOx emissions with the empirical N2O to NOx emissions ratio derived from the CalNex aircraft data. And then we can evaluate the satellite inferred N2O emissions by comparing with these independent studies. So that's what we've done now. We'll go through and look at these one by one. This is comparisons with that Lawrence study, which was an independent set of chamber measurements. We compare across all of May through September of 2018 and 2019 for any day when both the chambers were reporting measurements and when the satellite was able to make observations. It's a box and whiskers plots. The blue shows the chamber N2O flux from the Lawrence study. The orange to red color shows the Tropomi N2O flux derived with this proxy satellite method. And you can see there's really close agreement across these different methods in terms of the mean, the median, and actually the distribution themselves. In some ways, this actually looked like it agreed better than I might have expected, considering that the Lawrence study was really chamber-based, which is much smaller spatial scale than the satellite study. So we are measuring things on different scales, but it seems like the satellite estimate approach is able to give numbers commensurate with that produced by chambers in the region. Next, we compare with the airborne sampling that was done in the Dot-Cheech study. So this is quite a different comparison. So we actually only have 5 days in May and June of 2021 and 2022, where there both was flight data collected and we have satellite data to do quantification. So it's a much smaller number of days and a much statistically weaker comparison because of that. In this case, the aircraft flew at low altitudes, kind of rastering around these agricultural fields, and then actually atmospheric transport modeling and inverse modeling was used to actually produce gridded N2O fluxes to match the observations from the aircraft. So we then aggregate those up and try to compare them with the tropomi fluxes. And what we see is that the estimates from satellite encompass most of the estimated emissions from the aircraft. So the red is again tropomi, the maize N2O fluxes that derive from the aircraft. But we see not nearly the same level of close agreement we saw before. It's possible this is just due to data limitation because it's a really small number of days. It's possible this is related to some faulty assumptions in the N2O to NOx emissions ratio. It's possibly because the satellite maybe doesn't capture some of the high-end emissions from small regions that contributes to significantly to the high emissions seen by the aircraft, or a different phenomenon. But the good news is that in general, it tends to encompass within the magnitudes in its error bounds. And then finally, we compared it in the Mississippi River Valley. And here we looked at actually monthly emissions estimates. And part of why we did this is that aircraft campaign did larger mass balance calculations over large regions. And that aircraft campaign is shown here in the red dot. Whereas then I'm showing estimated N2O emissions inferred from the satellite approach over the course of a full seasonal cycle here. You actually can see there's pretty close agreement between that red dot and the black dot next door. So there seems to be relatively good agreement with this aircraft mass balance approach and the tropomi derived emissions estimate. There is a very large confidence interval here, right, on our satellite method. That's that gray band. That large confidence interval is really driven primarily by this range that exists in the N2O to NOx emissions relationship. I told you we kind of get a population there, and that population is pretty broad, and that's what defines the breadth here in the uncertainty. So I would say if we take this in aggregate, it really suggests that I think this is a viable approach that we could use. Refinement of the N2O to NOx emissions relationship would likely be the next step to improve this. And this would require more measurements of N2O and NOx made at those commensurate scales, which hasn't been done very much. And just as a final example, and this won't take me too long, so we should have adequate time for questions, I want to talk a little bit about refrigerants. Refrigerant needs are increasing, right? We have increase in urban populations, urban temperatures are increasing, populations in hot climates are increasing, and all this leads to increase in air conditioning needs. Heat pumps are and will continue to displace combustion heating, and these require very large refrigerant loads to function, and then they cycle a lot more often than air conditioners. Historical refrigerants have really had very large environmental impacts, famously with ozone, also with climate. The next generation of refrigerants carries some risks when we talk about things like HFOs or ammonia. Limited work has really been done to determine emissions from end use. It is impactful for urban policy if you want to care about the emissions of either your climate or air quality relevant gas in your urban domain. It's potentially impactful for urban air quality and health when we start to talk about gases like ammonia. And it's also important for mitigation. If we don't understand where these gases are emitted from, we might inadvertently build infrastructure that emits a lot more of these in the future. So to study this, we actually were able to look back at our eco data. So this shows a photo from that eco campaign flying around New York City to be able to actually really assess halocarbon emissions from the city. And it's a relatively simple concept as what we did with methane. So it's the same low and slow aircraft flights. Here we have the winds coming from the southwest. We have a cross-section flown downwind of New York City. You see in CO2, there's elevated CO2 in this urban plume. On the upper right here, it shows that time series of CO2. And the X shows when we have flask samples. So we had continuous measurements of things like CO2 and methane. We also took flask samples, and those were triggered manually on the aircraft, in the plume and outside the plume. And the idea here is we can then look at the enhancement ratio of any gas we could measure in the flask. And these flasks get sent back to NOAA, and lots of gases are measured in these flasks. We actually use the fact that we have continuous methane as a test to make sure these are representative of the whole urban plume. So if the flask sample gives the same methane to CO2 and methane to CO emissions ratio as the continuous data would give us, then we think it's a representative sample. And then we can quantify the emissions with this equation of really any gas that we've measured in the flask that shows a statistically significant enhancement in that urban plume. So we looked across primarily the halocarbons, and we see that there's robust enhancements, so on the orders of tens to hundreds of ppt, for many HFCs and HCFC species downwind of New York City. That's shown in panel A here on the upper left. On the upper right, I show a number of CFCs, halons, PFCs. These are gases where we did not measure a significant enhancement in the plume relative to outside of it. Doesn't mean that there's not emissions, it just means that we aren't able to measure and detect it robustly. And the relative enhancement is shown on the bottom. So you can see these tens to hundreds of ppts correspond to roughly 10 to 100% relative enhancement of these gases. So we basically can translate these urban enhancements into emissions combined with the CO2 observations, CO2 emissions inventory, and the relative molar masses. When we do this, we find that observed emissions exceed inventories when the inventories exist. So you can see here estimated emissions rate for a number of HFCs and HCFCs. The blue shows from flights in 2018. The green shows from flights in 2020. The X and the triangle show the EDGAR inventory estimates when they exist for those 2 different years. And then the dashed dotted line shows the EPA emissions estimate for the entirety of the state of New York and New Jersey. So what you see is that when inventories exist, and they don't always exist for these gases, they tend to underestimate emissions, right? The EDGAR ones are consistently less than what we see in the aircraft. And actually, we see for many of these gases that the emissions from this urban region itself are higher than the estimated emissions by the EPA of the entirety of the state of New York and New Jersey. So these are significant emissions. We started to try to look at what is going on here to better understand this by comparing a little bit with NOAA's emissions tracker. So what NOAA does is they take flask measurements around the US and do some inverse modeling to assess emissions of a number of HFCs. They don't have any measurements in New York City or directly downwind of New York City. But what we could do is compare their estimated emissions for the entire Northeast region and create a per capita emissions and compare that with the per capita emissions we observe in the city. That's what's shown here for these HFCs they report estimated emissions on. And you can see remarkably close agreement between our HFC estimates and the estimates from NOAA's emissions tracker when we consider per capita emissions. So this suggests a couple things. One is the emissions magnitudes we see are not kind of crazy or out of line or out of consistency with other observations and methods. It also suggests cities are not a special source. It's not that the city is doing something particularly unusual or crazy to emit so much of this gas. It's more that emissions follow the people. There are more air conditioners, refrigerators, and so on that track the people. And so when there's more people in the city, there's more concentrated emissions there. This actually makes it an ideal measurement environment because you get larger signal to noise to really study and understand emissions that might even be of low magnitude. What's the impact of that emissions? Well, most of these gases matter most as climate gases. They have large global warming potential. If we actually look at the CO2 equivalent emissions of halocarbons and methane from the city, that's shown here on the left, this is with a 100-year global warming potential. The emissions of halocarbon from the city have comparable impact to that of methane emissions, actually maybe slightly higher. This is about 10% of the CO2 emissions from the city. And if you use a 20-year global warming potential, you then would estimate that the contribution is roughly 25% that of CO2. So these are significant climate emissions of gases. And it really shows that the end use emissions are maybe more important than often realized. We actually can start to see temperature relationships here. So the data is limited, but it's worth exploring and seeing what was emerging in the data. So here we have HCFC 22 and HFC 134A. These are both used in air conditioning. And on days we flew when the air temperature was above 70 degrees, we tend to see higher emissions than on days we flew when the temperature was in the 50s. Gases like methane or HFC 152A, not used in air conditioning, do not show this relationship. What does this mean? Well, it's suggestive that perhaps that when air conditioners are actively used and cycled, emissions are higher. This is not accounted for in many inventories. It's maybe part of why the inventories are low. And it also makes physical sense that when you're actively cycling the refrigerant, you might be emitting more than when it's sitting idle. It's pertinent, though, especially as we consider future usage of things like heat pumps and high refrigerant loads. If there's higher emissions than we realize when these appliances are used, this is something we might need to account for and might need to consider in our installation and maintenance. And I'll finally make the point that these airborne observations can really uncover unrealized impacts of current emissions, as shown here. I think similar observations could assess emissions and atmospheric impacts of next generation refrigerants and other emergent pollutants. And this is really a good proxy and a good approach to get at that. All right, I'll wrap up now, and then I'll happily take any questions people have. So what are my concluding thoughts? Well, our ability to observe and identify and quantify the impacts of various gases on the atmosphere has really improved, right? As human systems are changing, as natural systems are dynamically responding, we're really improving our ability to constrain and understand this, but this requires ongoing investments and observations to continue. And we right now are at a point in time where it seems like that might not be the case. And if we have a big reduction in investment and observations, we might really lose our ability to understand what is happening dynamically in the atmosphere at a time when things are changing quite rapidly. For methane, with continuity of observations, I think we can really start to nail down what's happening with urban inputs from space. I think this has relevance for both policy and for understanding global trends in methane. Excuse me. We are getting closer to tackling tropical wetland emissions behavior for methane, but we're not there yet. And we really need expanded and improved tropical observations to nail this down, I think. Nitrogen from croplands is really only going to be of growing importance moving forward. I think we have pathways to better observe and understand this here, but again, this is a space where more investment is going to be needed. And finally, refrigerants, our old friend in the atmospheric chemistry community, still might have important atmospheric impacts. But with the right measurements, I think we should be able to identify this and then be able to inform smart actions on behalf of humanity moving forward with that regard. With that, thank you very much for your attention. I'm happy to take any questions people have. Thank you.
Thank you. So if you have a question for Eric, you can go ahead and raise your hand to ask it. Everyone should have the ability to unmute yourselves. Otherwise, you can type your question in the chat and I will read it aloud.
So Eric, this is John. Very informative talk. So as far as methane emissions in the cities, I assume they could come from both residential and industrial sources. So like which part is dominant?
Was that for methane or for refrigerants or all of the above?
Methane?
Methane? Yeah, I mean, so cities aggregate a lot. And actually, the approach that we take with tropomi, we really look at not just a small swath of the urban core, but we actually look at a very large domain, including kind of the immediate suburbs as well. So that includes both households with their natural gas heat, landfills, and in some cases, it can even include wastewater treatment. And sometimes there can even be some agriculture that's right on the fringes of the city that can be captured there. All of those are important. It seems in the US that natural gas is often, especially in cities with big natural gas systems, is a dominant contributor. That we know that globally, a lot of these emissions are caused more by landfills as well. So I'd say those are probably the two biggest sources of methane in the urban environment that we see.
I see. Thanks.
Thank you. James, you can go ahead and ask your question.
Okay, thanks. Hi, Eric. It's good to see you. I was wondering regarding HFC emissions. So you found that the your airborne measurements suggest that the urban area emissions may be higher than reported in inventories. Now, have you looked into whether that means maybe the modeling that goes into the EPA inventory might kind of might underestimate underestimate the leak rate. So it kind of prolongs kind of lifetime of the refrigerants within the AC systems or AC equipment. And but then maybe if you integrate the emissions over time for a particular amount of HFC that's used, that might end up being the same amount. So maybe your measurements are suggesting a faster leak rate, and then that could mean more replacement of the refrigerant. But then if you account for the total amount of production of HFCs, over the lifetime, there still may be the same amount of emissions.
Yeah, so this is a great question. I mean, I view this as a life cycle type question, right? Because and I want to be clear that we're not trying to state that based on our observations that global emissions estimates are too low for some of these gases, right? We can't conclude that from our observations of New York City in some ways because of what you're saying, right? Just because the emissions are higher from this part of the life cycle doesn't necessarily mean that emissions over the full life cycle are different from what's estimated in inventories. We don't have the data along the whole life cycle to be able to say exactly what's going on there. For the most part, I would say historically our concern about refrigerants has been an integrated global signal because the large impact has been climate and has before that, right, it's ozone, right? And so the way the atmospheric chemistry community has set about to understand this is with kind of remote monitoring to see global levels that increase kind of slowly over time. And then you can match whether globally the inventories emissions relatively match the growth rate we see in the atmosphere. So the work we're doing here doesn't suggest any of that work is wrong or invalid at all. What it does suggest is that if we start to go and get at what are the processes and where are the emissions that are emergent from, we can start to uncover some surprises, which can be relevant for mitigation, right? This does not mean that the life cycle estimated emissions are necessarily wrong in the inventory. It's really hard to compare with some of the inventories that are done for reporting purposes and this spatial scale, right? There's a reason I showed the EPA estimate for all of New York State and New Jersey because there isn't a gridded inventory that's resolved at a smaller scale than that. EDGAR grids at a smaller scale, but it doesn't align with the official reported inventory, right? Now, the discrepancies we see are such that we know emissions must be higher because if we see higher emissions from New York City than from the entirety of New York and New Jersey, it must be a problem with the inventory in that account and in that regards. So that was somewhat of a long answer, but I think it tries to get a little bit at what you're talking about. I think that especially when we consider future refrigerants, so when we talk about HFOs or ammonia, these are more reactive gases. Global sampling is not going to tell us what's happening. We're going to need to see what's happening closer to where emissions are occurring. And this is part of where I think actually these types of urban observations are going to be really important to understand if emissions are what we think they are and what the impacts of that will be.
I see. Thanks.
There's another question in the chat. Is it a LiDAR-based system that is used in data collection?
So I talked about a number of different data collection systems, but none of the ones I talked about today are LiDAR, so I can answer that broadly. The different measurement systems that I showed here today kind of range from various in situ measurements. So on the aircraft, the measurements of, for example, methane and carbon dioxide are made by cavity ring down spectrometer. Those were made by a Picaro instrument. The ethane measurements were made with an Airdyne. These are laser-based spectrometers. The satellite remote sensing that I mostly showed you, like the data of methane, NO2, methane and CO is made by looking at backscattered solar radiation in the shortwave infrared. NO2 is similar, but it's at different wavelengths. It's not in the shortwave infrared. And then the GPS antenna stuff for inundation, that's an L band. That's much longer wavelength. But none of those are active LiDAR systems.
Thank you. Does anyone have any other questions? Again, go ahead, James.
Thanks. Well, I might as well ask another question. So Eric, I was wondering, have you done any more measurements recently of upstream emissions from the oil and gas industry, like yeah, from oil and gas production areas and processing plants and things like that?
Yeah, obviously my group has done a lot of work looking at oil and gas, methane emissions over the years. We've not recently been making any more in situ airborne observations. Our work on that thread has been more, we've been collaborating with Adam Brandt's group at Stanford with doing controlled releases of methane to test, evaluate, and improve airborne and space-based remote sensing of methane point source emissions. So that's where our work has been in that space recently, has really been trying to better understand and improve our ability to, from space, be able to quantify point sources of methane and be able to extrapolate that work more broadly.
I see. Okay, thanks. Yeah, I thought the work you did in the past on like airborne measurements of like methane and I think maybe black carbon also from flares, that was really interesting. So I was just curious whether you had you've done any more work along those lines.
Yeah, not recently, but thanks, James. It's appreciated.
Sure, yeah.
Do we have any last questions just before we finish up? It's past 3 now, so we're about due. Okay. Well, in that case, thank you everyone for attending. Thanks so much to Eric for giving us this great talk. As a reminder, our seminar series, we do have one that's on Thursday. That one is in person. You'll have an email from John in your inbox about that already, and you'll get another one tomorrow. And then after that, we will resume our Monday schedule. So thank you so much, everybody. Have a great rest of your day.